On a quiet January evening in 2014, the night sky over Papua New Guinea erupted in a blaze of light. A fireball, unlike any other, tore through Earth's atmosphere at a staggering 45 kilometers per second, far faster than any typical meteor. This was no ordinary space rock. It was moving too quickly, its trajectory too strange, its resilience too extraordinary. Most meteors would have shattered high above the planet, but this one held strong until it reached just 17 kilometers above the surface. For years, this event lingered as a curious data point in US military records, a fleeting anomaly tracked by satellites. But in 2019, Harvard astrophysicist Avi Loeb caught wind of it, and what began as a footnote in government logs transformed into a quest that could redefine humanity's place in the cosmos. Imagine standing on a beach, staring out at the endless Pacific, knowing that somewhere beneath those waves lies evidence of a visitor from another star system. Not a signal, not a theory, but physical fragments you could hold in your hand. This is the story of IM-1, officially designated CNEOS 2014-01-08, a meteor confirmed by the US Space Command in 2022 with 99.999% certainty to have originated beyond our solar system. That's not a typo, military-grade confidence that this object came from the depths of interstellar space. But what makes this discovery electrifying isn't just its origin, it's the possibility that what crashed into our ocean might not be a simple rock, but a remnant of something engineered, perhaps by an intelligence we've yet to comprehend. In June 2023, Avi Loeb and his team at Harvard's Galileo project set sail aboard the Silver Star, bound for a patch of ocean 84 kilometers north of Manus Island. Their mission? To recover fragments of IM-1, the interstellar fireball that had captivated scientists and sparked wild speculation. Armed with a tool they dubbed the Interstellar Hook, a weighted sled lined with powerful magnets, they scoured the Pacific seafloor for 2 grueling weeks. The ocean floor, a vast and unforgiving abyss, held secrets buried under layers of sediment. Yet, along the calculated path of the 2014 fireball, they found something extraordinary. 850 tiny metallic spheres, each no larger than a grain of sand, shimmering like cosmic marbles. These weren't just any particles. Under the microscope, they revealed a story of unimaginable violence and heat, droplets of metal forged in the inferno of atmospheric entry. But what stunned the team wasn't their size or shape, it was their composition. About 10% of these spherules, classified as Belaeu-type particles, contained elemental ratios of iron, magnesium, and titanium enhanced by factors of 10 to 1,000 times compared to anything found on Earth, the Moon, or Mars. Unlike typical meteorites, which are rich in nickel, these spheres had almost none. Their chemical fingerprint was alien in every sense of the word, defying every known natural source in our solar system. Picture this, a scientist in a lab peering through a microscope at a speck of metal smaller than a poppy seed. It's not just a rock, it's a relic from another star system, a fragment that traveled millions, perhaps billions of years to land in our hands. The implications are staggering. Could these be natural debris from a distant planet? Or could they be something more? A piece of technology crafted by an intelligence we can't yet fathom. The question isn't just scientific, it's existential. What if the first proof of extraterrestrial life isn't a signal from the stars, but a handful of molten droplets resting quietly on the ocean floor? The discovery of these spherules is a scientific first. No human has ever held confirmed material from beyond our solar system until now. Every meteorite in every museum, from the massive Hoba meteorite in Namibia to the tiny fragments in NASA's vaults, originated within our cosmic neighborhood. But IM-1 is different. Its speed, trajectory, and material strength set it apart. Most meteors burn up or shatter at altitudes far higher than 17 kilometers. IM-1's resilience suggests a toughness that surpasses anything in NASA's catalog of 272 known space rocks. This wasn't just a rock surviving a fiery plunge. It was a survivor of forces that should have obliterated it. The chemical makeup of these spherules only deepens the mystery. Their unusual combination of elements, high in iron, magnesium, and titanium, but low in nickel, doesn't match the profile of any known asteroid, comet, or planetary body. Scientists have compared them to everything from volcanic ash to industrial pollution, but nothing fits. fits. The Belle-Ique particles in particular are a conundrum. Their elemental ratios are so extreme that they hint at an origin in an environment unlike anything we've studied. Could they have formed in the crucible of a supernova? Or were they forged in a process we can't yet imagine, perhaps in a machine? The Galileo Project's expedition marks the first dedicated attempt to recover physical debris from an interstellar object, but it's not the first time our solar system has been visited by cosmic outsiders. In 2017, astronomers spotted Oumuamua, a cigar-shaped object that zipped through our system at breakneck speed. 2 years later, Comet Borisov became the second confirmed interstellar visitor, yet IM-1 stands alone. It's the only one that left tangible evidence behind, fragments we can touch and test. This raises a chilling question. How many other interstellar objects have struck Earth unnoticed? For 4.5 billion years, our planet has been a target for cosmic debris. Could our oceans already be littered with relics from other stars? The story takes a sharp turn when you consider who first noticed IM-1. It wasn't a team of astronomers gazing through telescopes. It was the US military. In 2022, US Space Command declassified data about the 2014 fireball, releasing a letter that confirmed its interstellar origin with near absolute certainty. But why would the military track a meteor so closely? And why declassify this information now? These aren't decisions made on a whim. The military's interests suggest there's more to IM-1 than meets the eye. Consider the strategic implications. A material tougher than any known meteorite, capable of surviving atmospheric entry when it should have vaporized, could revolutionize technology. Imagine alloys stronger than anything we've engineered, compounds that could transform aerospace, defense, or even energy production. IM-1's fragments, if artificial, could spark a new kind of space race, not for territory, but for materials. The fact that the military was watching so intently raises questions about what they know that we don't. Were they tracking IM-1 for its scientific value, or because it hinted at something with far-reaching implications? The discovery of IM-1 spherules echoes other pivotal moments in science. In the 1980s, scientists found microscopic glass beads in sediment layers worldwide, known as impact spherules. These tiny relics helped prove that an asteroid wiped out the dinosaurs 66 million years ago, rewriting Earth's history. In the 1970s, lunar meteorites found in Antarctica offered our first physical connection to the moon before Apollo missions brought back samples. The IM-1 spherules could be another such moment. A leap forward that transforms our understanding of the cosmos. 50 years from now, textbooks might look back on these droplets the way we now view the first moon rocks. They could mark the beginning of a new era in astronomy, where we don't just observe distant stars, but hold pieces of their worlds in our hands. These tiny beads, sitting unassumingly in a Harvard lab, could be humanity's first physical package from another star system. They're not just rocks, they're messages in a bottle carried across the galaxy to find us. The story doesn't end here. In 2025, Avi Loeb and his team plan to return to the Pacific with an underwater robot, the ROV Hercules, to search for larger fragments of IM-1. The spherules they've collected are like cosmic splatter, molten droplets from a violent atmospheric entry. But somewhere on the ocean floor, there could be chunks of the original object itself. A piece large enough could reveal its age through radiometric dating, pinpoint its origins through isotopic analysis, or even expose structural features that hint at artificial design. Imagine recovering a fragment the size of a fist, its surface etched with patterns that couldn't form naturally, layers, circuits, or alloys, unlike anything in our periodic table. Such a find would be more than a scientific curiosity, it would be a paradigm shift. We could learn about the chemistry of distant planetary systems, discover new materials, or, in the most profound scenario, uncover evidence of alien engineering. The implications stretch beyond astronomy to technology, philosophy, and our very sense of identity. Are we alone, or are we part of a cosmic tapestry woven with threads from countless stars? The discovery of IM-1 raises questions that go beyond material science. Some scientists propose that interstellar debris could carry the seeds of life itself, a concept known as panspermia. Imagine the wonder of learning that life on Earth began with molecules delivered from another star system. Our existence could be tied to the cosmos in ways we've never imagined. If IM-1's spherules are natural, they might still reveal the chemistry of distant worlds. If they're artificial, they could open a door to technologies we can't yet dream of. The search for answers continues. Isotope analysis, underway as of September 2025, could confirm whether these particles formed around our sun or a distant star. Skeptics argue they might be terrestrial contaminants, coal ash, volcanic particles. These concerns are valid, and rigorous testing is essential, but the Galileo Project's work is groundbreaking regardless of the outcome. As of September 22, 2025, the debate surrounding the IM-1 spherules has intensified, with Harvard's A.V. Loeb publishing a detailed refutation of skeptical claims that these mysterious metallic droplets could be explained away as common terrestrial materials like coal ash or Australasian tektites. In a comprehensive analysis shared on his Medium blog on September 13, 2025, Loeb and his team meticulously compared the elemental compositions of the Balayu-type spherules, named for their unusual enrichment in beryllium, lanthanum, and uranium, to a wide array of known Earth-based contaminants and natural formations. Through advanced laboratory techniques, including X-ray fluorescence and mass spectrometry, they demonstrated irrefutable differences in isotopic ratios and trace element patterns that set these spherules apart from anything produced by human industry or geological processes on our planet. For instance, while coal ash might exhibit elevated levels of certain heavy metals due to combustion byproducts, the specific beryllium enhancement in the Balayu particles, up to 1,000 times higher than in terrestrial samples, defies any coal-derived explanation, as beryllium is not a common component in fossil fuels or their residues. Similarly, comparisons to tektites, which are glassy objects formed from meteorite impacts on Earth, revealed stark contrasts in magnesium and titanium abundances, with the IM-1 fragments showing a unique depletion in nickel that is absent in tektites. This painstaking work not only bolsters the case for an interstellar origin, but also underscores the importance of open-minded inquiry in science, where initial skepticism can lead to deeper truths when met with empirical evidence. The Galileo Project's ongoing efforts, now bolstered by these findings, have sparked renewed interest among astronomers and materials scientists worldwide, prompting collaborations with institutions like NASA's Jet Propulsion Laboratory to explore potential applications of these exotic compositions in advanced engineering. Imagine the ripple effects. If these spherules truly hail from another star system, their study could unlock secrets of cosmic nucleosynthesis, revealing how elements are forged in the hearts of distant stars, or even in the remnants of ancient supernovae. Beyond the lab, this refutation has cultural ramifications, challenging humanity's anthropocentric view of the universe, and inviting us to consider that our solar system might be a mere pit stop for wandering cosmic artifacts, each carrying stories of far-off worlds, and perhaps even the echoes of long-extinct civilizations. As Loeb emphasizes, dismissing these findings without rigorous examination is akin to ignoring a message washed ashore in a bottle, simply because it challenges our preconceived notions of isolation in the cosmos. With isotope analysis nearing completion, the scientific community awaits results that could definitively trace the spherule's birthplace to a star light years away, potentially rewriting textbooks on planetary formation and interstellar travel. Building on the momentum from IM-1, the year 2025 has brought fresh excitement with the detection of another interstellar interloper, Comet 3I/ATLAS, which has captured the imagination of scientists and the public alike with its peculiar trajectory and size, comparable to Manhattan Island, prompting speculation from Avi Loeb about its potential artificial nature. Discovered hurtling toward our solar system at an anomalous speed, 3I/ATLAS exhibits orbital characteristics that deviate from those of typical comets born within our cosmic neighborhood, raising questions about whether it could be a probe or spacecraft dispatched by an extraterrestrial intelligence, much like the theories surrounding Oumuamua in 2017. In a co-authored research paper published in July 2025, Loeb explores the possibility that this massive object might release smaller mini-probes as it approaches Earth between November 21st and December 5th, 2025, which could manifest as unidentified anomalous phenomena UAPS in our skies, urging NASA and other space agencies to monitor its passage closely for any unusual emissions or maneuvers. This hypothesis, while bold, draws from the same scientific rigor applied to IM-1, analyzing the comet's hyperbolic orbit, a telltale sign of interstellar origin, and its lack of a traditional cometary tail, which might indicate a non-natural composition or propulsion system. The Galileo Project, ever vigilant, has pivoted resources to track 3 3I/ATLAS using ground-based telescopes and satellite data, aiming to detect any signals or structural anomalies that could hint at technological artifacts. This development amplifies the narrative of IM-1, suggesting that our solar system is a frequent waypoint for cosmic wanderers, each potentially bearing clues to the broader galactic ecosystem. If 3I/ATLAS does deploy probes, it could provide real-time evidence of alien exploration, transforming abstract theories into observable events and galvanizing global efforts to establish protocols for first contact. Moreover, the intersection of these discoveries highlights a burgeoning field of interstellar archaeology, where scientists like Loeb advocate for proactive searches rather than passive observation, proposing missions to intercept future visitors with robotic explorers equipped with spectrometers and imaging tools. The implications extend to philosophy and ethics. How do we respond if 3I/ATLAS proves artificial? Would it signal peaceful curiosity or something more ominous? As September 2025 unfolds, with Loeb's team preparing for potential follow-up expeditions inspired by IM-1's success, the anticipation builds, reminding us that the universe is not a static backdrop, but a dynamic arena teeming with possibilities, where each new object could be a key to unlocking the mysteries of existence itself. Looking ahead, the second half of 2025 promises a surge in exploratory endeavors, as outlined by Avi Loeb in his June 18, 2025 essay, emphasizing expanded opportunities to scour our cosmic mailbox for more interstellar packages like IM-1, with plans for deploying the ROV Hercules to revisit the Pacific site in search of larger IM-1 fragments. The Galileo project is gearing up for a mission that could yield chunks substantial enough for detailed structural analysis, potentially revealing layered compositions or engineered features that the tiny spherules only hint at. This ambitious return, building on the 2023 expedition's magnetic sled successes, incorporates cutting-edge robotics and AI-driven mapping to navigate the challenging seafloor terrain, where currents and sediment have guarded these secrets for over a decade. Loeb's vision extends beyond IM-1, advocating for a fleet of ocean-going vessels equipped with advanced sensors to systematically survey impact zones of other potential interstellar meteors, transforming the Earth's oceans into vast archives of galactic history. The integration of new technologies, such as high-resolution sonar and autonomous underwater vehicles, aims to increase recovery efficiency, allowing scientists to collect samples that could undergo comprehensive testing for isotopic signatures unique to extrasolar environments. Furthermore, collaborations with private entities like SpaceX, echoing Elon Musk's interest in alien remnants, could accelerate these efforts, perhaps even inspiring Mars missions to hunt for similar Balayu-type materials on the red planet's surface, as speculated in recent discussions. This multifaceted approach not only addresses lingering skepticism by amassing more data, but also fosters interdisciplinary innovation, blending oceanography, astrophysics, and material science to push the boundaries of human knowledge. As these expeditions unfold, they carry the emotional weight of discovery, evoking the thrill of explorers like Columbus or Magellan, but on a cosmic scale where each retrieved fragment could narrate tales of stellar births, planetary evolutions, or intelligent designs from afar. The potential for breakthroughs in 2025 and beyond underscores a pivotal shift in astronomy, from skyward gazes to hands-on investigations, where touching the stars becomes literal, inspiring generations to dream bigger and question deeper about our place in the infinite expanse. The discovery of IM-1 and the anticipation surrounding 3I/ATLAS are not just scientific milestones. They're igniting a global awakening, stirring the collective imagination of humanity in ways few discoveries have. Across social media platforms, posts from users in 2025 reflect a growing fascination with the possibility that we're on the cusp of contact with something beyond our world, with trending hashtags like interstellar messages and cosmic clues amassing millions of views. This isn't just about scientists in labs or robots scouring the ocean floor. It's about people from all walks of life, teachers in rural classrooms, engineers in bustling cities, and dreamers gazing at the stars, connecting with the idea that we might not be alone. The Galileo Project's work has transcended academic circles, inspiring artists to create murals of glowing meteors, musicians to compose symphonies echoing the hum of the cosmos, and educators to rewrite lesson plans that now include interstellar archaeology as a field of study. This cultural shift is palpable as communities worldwide host stargazing events and virtual forums to discuss what it means to hold a piece of another star system. The emotional resonance of this moment lies in its universality. Every human, regardless of background, can relate to the question of our place in the universe. If these spherules or future fragments prove artificial, the impact would ripple through religion, philosophy, and governance, prompting debates about how we define life, intelligence, and our responsibilities as cosmic citizens. Even if they're natural, they offer a humbling reminder of our planet's smallness in the grand tapestry of existence, urging us to protect our fragile world while reaching for the stars. The Galileo Project's transparency, sharing updates through accessible platforms, has democratized this discovery, inviting everyone to participate in the wonder. As we await the 2025 expedition's results, this moment feels like a shared journey where each new finding, whether a chemical anomaly or a larger fragment, brings us closer to answering humanity's oldest question: are we alone? This collective anticipation is a powerful force, uniting us in curiosity and hope as we stand on the shore of the cosmic ocean, ready to receive its next message. The pursuit of IM-1's secrets and the tracking of 3I/ATLAS are laying the foundation for a legacy that could shape humanity's future for centuries. The Galileo Project's work is not just about one meteor or one comet. It's about redefining how we explore the cosmos, moving from passive observation to active engagement with the universe's artifacts. The technological advancements driven by this search, from AI-enhanced underwater robots to next-generation spectrometers, are already spawning innovations that could transform industries on Earth, from deep-sea exploration to materials engineering. Imagine a future where alloys inspired by IM-1's spherul's power spacecraft capable of interstellar travel, or where isotopic analysis techniques developed for these fragments unlock new ways to harness energy. Beyond technology, this quest is reshaping education and policy, with universities launching interdisciplinary programs in astromaterials and governments beginning to draft frameworks for handling potential extraterrestrial artifacts, inspired by discussions about regulating AI autonomy events. The possibility of finding engineered structures in larger IM-1 fragments or signals from 3I/ATLAS is sparking ethical debates about how we'd interact with an alien civilization. Would we broadcast our presence or listen in silence? These questions are no longer science fiction. They're becoming practical considerations as our tools and ambitions grow. The cultural impact is equally profound, with younger generations inspired to pursue STEM careers, driven by the thrill of touching the stars. Museums are already planning exhibits to showcase replicas of the IM-1 spherules, alongside narratives of how they were found, ensuring that this story becomes part of our shared heritage. If the 2025 expedition uncovers larger fragments, or if 3I/ATLAS reveals signs of artificiality, the legacy of this moment will echo through history, much like the Apollo missions or the discovery of DNA. It's a reminder that exploration is not just about finding answers. It's about asking bolder questions, daring to imagine that our planet is but one chapter in a vast cosmic story. As we stand on the brink of these discoveries, we're not just scientists or spectators. We're storytellers, weaving a narrative that could inspire humanity to reach beyond our world, carrying the dreams of today into the stars of tomorrow. This is a moment to pause and marvel. The boundary between Earth and the cosmos is more permeable than we ever imagined. These tiny spherules, forged in the fires of a distant star, traveled unimaginable distances to land in our hands. They remind us that discovery isn't confined to telescopes or spaceships. Sometimes it's hiding beneath the waves, waiting for us to find it. The search for IM-1's origins is a testament to human curiosity, a reminder that the universe is full of mysteries we're only beginning to unravel. What do you think? Are these spherules just cosmic curiosities, or could they be fragments of something far greater? Drop your thoughts in the comments and join the conversation. If this story sparked your imagination, hit the like button to spread the wonder, and subscribe to stay updated on the next chapter of this cosmic journey. The 2025 expedition could reveal findings that change everything. Maybe these are just interstellar pebbles, or maybe, just maybe, they're messages from the stars waiting for us to decode them.